Four charged particles are at the corners of a square of side small a as shown in figure. Determine the electric field at the location of charge minus q. So at here we need to determine the electric field and also the total force exerted on q. So this is the q. At here only we need to figure it out what is the total force due to because of these three charges. My humble suggestion before solving this problem, first you figure it out what is the direction of the electric field where you want to find it out by bringing coordinate system, or it is easy to use unit vectors. Okay, so for that I need to redraw figure. So I wish I can take this figure. So let me enlarge this figure at here. I wish to draw a coordinate system to figure it out what is the resultant direction. So I bring a coordinate system at here to the charge plus q. So let me place it here. Now I would like to write what are the forces. Now these two both are the positive charge. Two q and 2q. So these two are the positive charges. So this will repel each other. So this is the force along in this direction. So if it is a positive x-axis, I can assign the unit vector along in this direction. And due to plus 4q charge on the plus q charge, so what is the resultant electric field? Since they both are the positive, so this is the resultant electric field. So this is the unit vector j cap. And here you can see the third charge 3q is at diagonal. So if you make the diagonal from here to there, now where is the resultant direction? The resultant direction is along in this direction. Now this is something different and it is having in the two coordinates. So if I represent the resultant direction, this is the direction and this is in the xy coordinate. It means this is resolved into two components, depends upon the angle. So at here, since it is a triangle, if it is 90 degrees and this angle is 45 degrees and the same 45 degrees will be at there. Now if you take, this is charge q1 and charge q2 and charge q3. Now q2 charge is resolved into two components. The component along x-axis let me take my pen. So one of the component is the component along x-axis. So to highlight, this is the component along x-axis component and the same the component along y-axis. So this is the previous knowledge we already did in the vectors. So horizontal component we will take in terms of the cos theta and vertical component we will take in terms of the sin theta. Now where would be the resultant directions? The resultant direction will be the algebraic sum of all this. So I hope you understand the figure, how to draw. First of all, how to figure it out what is the resultant electric field directions. Now if I write by using principle of superposition. What is the electric field due to these three charges at here at the charge q? So that I can write as the electric field at charge q is given by, we can represent the total electric field E bar equal to electric field due to charge q1, that I can write as k times q1 times the distance from here to there I can take as r1 square, and I can represent the direction also along the unit vector r1 cap, plus for the second charge electric field due to second charge, here algebraic sum, so I need not to take anything of that. Now k times for the second charge k times charge q2 by r2 square unit vector direction r2 cap plus k times charge q3 by r3 square and unit vector direction r3 cap. Okay, so this is the general formula we used to use to calculate the resultant electric field due to combination of the system of charges. Now here I need to substitute each charge, what is q1 at here, 2q given there, now what is the q2, 3q, what is the q3, 4q, what is the r1, r2, r3. So these three distances I need to substitute. So the total electric field, the resultant electric field, if I write E bar equal to vector E k times, here the q1, here it is the value 2q. So 2q by r1 square, distance between these two charges. The distance between these two charges is just a square. And the direction, here the r1 cap is the direction, but here the direction I have taken along the unit vector direction I cap, plus k times, here the q2 is the charge, this is the q2 which I have taken, charge 3q by r2 square, means this is the distance from here to here, the diagonal. So you can use the Pythagorean theorem. By Pythagorean theorem, this distance r equal to square root of a square plus a square, it becomes 2a square. But in the formula it's the r square, it means it is gives as a 2a square. And the direction, here it is important because this vector is resolved into two components. So for that I need to write the components along I cap cos 45 degree plus j cap sin 45 degree. So these two terms came into picture because of this is the vector in the xy plane. So any vector in this plane will resolve into two components. And if we can write the electric field due to the third vector, the electric field due to the third we can represent as the third one plus k times q3, here the q3 is 4q by r3 is the distance is just a square, and r3 cap means this is the unit vector direction. Unit vector direction, here it is j cap. Now the problem becomes easy. We can pull it out, common factors. So I would like to substitute this cos and sin values at here. So k times 2q by a square along I cap plus k 3q by 2a square I cap cos 45 1 over root 2 plus k 3q by 2a square j cap sin 45 1 over root 2 plus 4k 4q by a square j cap. Now for the further simplification, just common I cap terms. So if I common I cap terms, so k q by a square is common in this one, so I can get it here. It is a 2 I cap plus, so if I take it out, 2 k q by 3a square, here I can get 3 by 2 root 2 I cap. I wish I can pull I cap outside and I can represent that I cap unit vector. Plus, similarly I can do the same for this another two terms, k q by a square. If you can take it out, that there I can get k q by a square, here I can get 3 by 2 root 2 plus 4 at here common j cap. If we can do simplification in these terms, so we can end up electric field E bar equal to k q by a square. This will becomes 3.06 I cap plus k q by a square, and this also will become 5.06 times j cap. So together we can write electric field E bar equal to k q by a square of 3.06 I cap plus 5.06 j cap. So this is the expression for the resultant electric field at charge q along with the direction. Now there itself you need to find what is the force. For the big question, you need to figure it out, what is the force at there itself. For the force and the electric field expression, we know that, if you can see the problem once again, so I wish I want to show you the problem once again. For the big question, the total force exerted on q, it means at here charge q, what is the total force, that we need to find it out. Since we already derived what is the expression for electric field there, so it is easy to find force because we know the relation between force and electric field. So the force means electric force. I should write it here. It is the electric force on charge q is given by the relation between force and electric field equal to force equal to charge times electric field, F equal to QE. And F equal to, we know that what is the charge q itself, what is the electric field, here I got it, electric field equal to kq by a square of 3.06 I cap plus 5.06 j cap. For simplification, sorry, so write the final expression. F bar equal to kq square by a square of 3.06 I cap plus 5.06 j cap. So this is the resultant force expression on charge q. So if you figure it out what is the electric field direction, so then it's easy to solve the rest of the things. So whenever you start to doing these electric field problems, first figure it out what its corresponding direction and direction.